a warm welcome again to this webinar, which is called Material-Driven Design High Performance Cold Plates, in which we hope you will have an overview of like an amazing project, Fraunhofer Push It Forward, leveraging the amazing CP1 material from Constellium and using ToffeeX to have a material-driven optimization. So hopefully towards the end of this presentation, you will have a grasp of how you can leverage the advantages of the material, of the innovative material Constellium is providing, and coupling this and leveraging the fluid dynamics of your cold plates in order to get very performant design in a very fast and quick way, and also in a way that is ready straight for manufacturing. So together with me, presenting this project, there will be Matthias from Fraunhofer and Sham from Constellium. So I will give the word to Matthias if he just want to briefly introduce himself and the company he comes from. And then maybe Matthias can hand it over to Sham for the presentation.
Yeah. Thank you, Nicola. My name is Matthias. I'm working for the Fraunhofer Institute for Forming Technology and Machine Tools in Germany, Dresden. I've been here since 2009, focusing on additive manufacturing. Since a couple of years, our department is called now Laser Powder Bed Fusion, since it's the only basically technology we are doing like hard research on. My main focus is finding new applications of this interesting technology, and especially the use of thermal management, or using this technology for thermal management. That goes from cooling for special toolings. It goes from applications like this one, like cold plates. It goes also like space application, printing heat pipes. Everything where we can use the freedom of design of additive manufacturing basically is my focus of research. Yeah, it's basically just a short introduction to give you an idea. I think if people have questions about laser powder bed fusion or the process itself, we sure can ask them later. So I might just hand over to Sham, and maybe you can say something about you and Constellium.
Thank you, Matthias, and thank you, Nicola. Hello, everyone. This is Sham Krishnan from Constellium. I'm working as a business development manager for the Constellium additive manufacturing team. Potentially, Constellium is an additive manufacturer, not an extra, mainly aluminum, a specialized company. And we have basically 3 business units in aerospace and automotive and packaging industry. And we roll out high value added products based on high and aluminum alloys. And additive manufacturing is one of our new comparatively new activity within Constellium. And we have around 27 factories spread across the globe. And additive manufacturing team is based in France. This is where our R&D team is located. We rolled out our material 2019, and since then, the CP1 material is experiencing a great growth. And today, I'm also excited to present the project that we have done together with the ToffeeX and the Fraunhofer team. Yeah, I'm looking forward for the presentation then. Thank you.
Thank you very much indeed, both Matthias and Sham. And again, if you have any questions related to the companies involved or the specific project, please drop us. You should have the option to drop us a message through a Q&A session, and we will go through them eventually. And eventually, there are always our email address. You can reach out to us quite freely. I think I speak also for Matthias and Sham. You can reach out to us without any problem. So without further ado, let's please jump into the presentation. And Matthias, if you would like to start, please, stage is yours.
Yes, I'm going to jump into the project. So I'm going to start to give you just a short introduction, the project's objectives. Then we're going to talk about the major part, the materials. we used, and that's also the main reason why Sham and Constellium are here. I'm gonna give you an overview about the design process, especially how we utilized the advantages of ToffeeX. I'm not gonna show you the whole printing process, just give you an idea and the machines we used. And then at the end, for us, it was interesting to analyze the printed parts and compare the results to the simulation. And I give you at the end, I think, a short conclusion, what we learned in this project and what the benefits are in the combination of ToffeeX Constellium and 3D printing. So for us, this project was mainly a benchmark study. On the one hand, we want to know about Constellium's Aheadd CP1 aluminum alloy in comparison to the standard aluminum silicon 10 that's widely used in additive manufacturing. And it is a casting alloy, aluminum silicon 10. So you can say it is basically the perfect material for the perfect job if you would have a casted part. But since 3D printing has got a bit different, it's a different process. We're bending the process to be able to use aluminum silicon 10 to some extent. That's why we are very interested in the CP1 from Constellium, because this material is especially designed for additive manufacturing. So it comes quite with some benefits. I think Sham will tell you guys more about this later. So yeah, that's basically about the objective for us, getting a comparison, what we can learn from CP1, Silicon 10, and then also we're always looking for new solutions, how we can give our customers improved performance and finding like faster and better ways to come up with the additive design. This can be very time consuming, and this is why we basically got in contact with ToffeeX and wanted to see how capable this software solution is. So for us, it was basically a good project to see where we can all benefit and how we can improve our process and our components at the end. Just shortly about the materials, you can see the main differences from the CP1 and aluminum silicon 10. Especially for this project, it is interesting. There's quite a difference in thermal conductivity. For the project, we used different parameters, mostly the density of the material, the thermal conductivity, and the heat capacity. This is the input values for the topology optimization using ToffeeX. You can see we calculate with the operating temperature of the cockpit around 100 degrees. That's why you see in the table the numbers down below. That's what we used as input for the simulation and for the project. And I think from here, I'm just going to hand over to Sham, and he's going to tell you more about the advantages of CP1.
I think, Sean, we cannot hear you.
Hello.
Okay, now we can, definitely.
Okay. So sorry for the technical glitch. Again, thank you, Matthias, for giving the short introduction about the project topic. And before we get into the details of the design and the component level testing, etc., I would like to give you all a small insight into the material properties and what you can expect from this material. So Aheadd CP1, so basically C stands for high conductivity and P stands for high productivity. This is an alloy that we have exclusively designed for laser powder bed fusion process. And it's an alloy of 98% pure aluminum and 1.1% zirconium and rust-use iron. And when we talk about aluminum 3D printing, most widely used material is aluminum silicon alloy. So CP1 is designed to overcome most of the problems associated printing aluminum silicon, or a component level application, if you can imagine. So when we talk about that in terms of productivity or surface finish or corrosion performance, whatever component properties that you can imagine, then CP1 is trying to solve all the problems associated with that. So in the tabular column, you can see the mechanical properties of this particular alloy. Contrary to aluminum silicon alloys, what you can see in the 0 hours, that means when you do a heat treatment of 400 degrees Celsius at 0 hours, which is as built, the alloy is really soft, which is 137 MPa, more than 20% elongation, low in thermal conductivity. But when we do a heat treatment of 400 degrees Celsius for 4 hours, the mechanical properties getting increased up to 300 MPa yield strength and more than 10% of elongation. Whereas the thermal conductivity and electrical conductivity goes up. There are ways we can still push it further, but this is a kind of property that is mostly used or mostly fitting in aluminum 3D printing application. So we believe CP1 is a drop-in replacement for any of the aluminum silicon or 6061 type applications. If we can go, yeah. So this particular image is really interesting. You can see on the y-axis yield strength and on the x-axis thermal conductivity plot for most of the aluminum alloy systems. So if you look at where CP1 is placed, this is the best trade-off that you can see, where you can have a reasonably good yield strength and very good thermal conductivity. No alloy is positioned in this kind of situation where we can still fine-tune the properties by adjusting the heat treatment. So CP1 will be able to address, I would say, 80% of the aluminum application that we can see in additive manufacturing world. Next slide, please. Yes. So one of the challenges people find when they print aluminum silicon is the anisotropy. Here in Aheadd CP1, when you print the components in most of the directions, you can see in the graph, X, Y, Z, or 45-degree angles in different planes, we see only a few MPa difference in all directions. This is a good promise for design engineers to give freedom to design components without restrictions coming from the material. And also, if the material is exposed to high temperatures, such as 200 degrees Celsius or 300 degrees Celsius for long duration, for let us say 4,000 hours, as we can see in the graph, the material never changes its microstructure. So if you cool down and test the material, you will see similar properties coming back to. So then what it exactly reflects on a component level application is that the life of the component or durability of the component goes for quite a long time compared to other aluminum alloy systems. This is an interesting property of Aheadd CP1, where based on the component design or property requirement, we can fine-tune the heat treatment, meaning as I explained earlier, in the as-built situation, the alloy is very soft, only 130 MPa. In the peak age, it's around 300 MPa. So there is a good amount of bandwidth where we can fine-tune the properties and to create a good trade-off between electrical conductivity and yield strength. So this will be really helpful to mimic different types of alloys, for example, or you wanted to maximize the electrical or thermal conductivity for thermal management application. This alloy brings a flexibility in terms of applications. Another important property of Aheadd CP1 is the outstanding corrosion and stress corrosion performance. When a design engineer design a component, he would like to make sure that the components survive extreme conditions, particularly on heat exchangers or heat sinks when those are exposed to extreme conditions. So when Aheadd CP1 compare its performance with its 6061 T6, that's one of the standard alloy in the market. You can see on the left-hand side, bottom area, CP1 is an outstanding performer in terms of corrosion. There is no visible attack for 24 hours immersion test. whereas 6061, you can see from the surface there is an attack happening, and CP1 really give good corrosion performance. Also, when the material is exposed to stress and in a corrosive environment, CP1 also provides very good stress corrosion performance. For example, you can see on the top right-hand corner, Aheadd CP1 heat treated 4 hours, 400 degrees. Even after 90 days of 90% yield strength applied, you don't see a sign of corrosion attack. Whereas the aerospace grade alloys like 2024 or 7 series alloys, it's almost completely corroded in this extreme condition. So if you're having an application that is exposed to very corrosive environment, CP1 could be the clear winner on this case. So in a nutshell, when we look at CP1, it's not only helping you to build structural component or some thermal component. You can combine applications, or you can create components integrated with the functionality. So basically, if you look at the composition, it's a simple composition. It's aluminum, zirconium, and iron. There is no rare earth, no expensive material. So the material is not that expensive. And at the end of the day, as there is no volatile elements, you are able to print the material very fast. If your printer is equipped with higher power, such as 700 watt or 1 kilowatt, so that brings down your component cost down because you are able to print fast. Then also the material is very much compatible with the large machine system, as there is no volatile elements, and also the material has very good thermal stability. So that means if you wanted to print a tall heat sink, you will not see a property gradation because the material is stable up to 350 degrees Celsius. And from an industrialization point of view, as it doesn't contain any kind of expensive material, it's easy to scale up, starting from few 100 kilograms to tens of tons of material. It's easy to industrialize. So the material, Constellium have defined or designed this material in view of enabling the customers to start integrating functions on the structural parts or even any other functional components. So this alloy is very versatile. So once you load the material on a machine, you can address multiple applications but without changing the material. So we believe there is a huge value addition coming from CP1 for users. So we will be seeing that very soon on the applications with Matthias is going to present it. From an industrial maturity point of view, the material is qualified on all of the most of the machines platforms in the market. For example, if you look at Nikon SLM solution in XT platform, SLM 500, 2ITs, or Velo 3D, both platforms, including the Sapphire XC, 3D systems, Trump, you name it. I mean, if you're having a machine, we will be able to support you to print the material in coordination with the machine builders. So from an industrialization maturity point of view, this material is seeing a high growth.
Yeah, thank you, Sham. I think it's quite impressive seeing the numbers, and especially in comparison to the conventional materials in use. So I think from this point on, we can go forward and show you more about the project, and you can see why we use this combination of material and process. The component itself, it's based on a real-world application we see quite regularly nowadays. Thermal management of electronic components or computing units or server units. So all this thermal management, these electronics or parts getting more and more performance, but it also goes along with more and more heat. We had some of these projects where we had to design a cooling solution for such a system. So we choose for this project that we have 4 different heat sources from 4 different heights, different positions in a computing unit, whatever. We choose a power input of 50 to 80 watts, what's quite similar to a CPU or sometimes even a GPU. And to get really the benefits out of ToffeeX, out of the use of ToffeeX, we decided to separate the part in basically in two different sides. There's one where we want to cool the system with natural convection, with free convection, and the rest of the part was meant to be cooled using water. So, and from there on, you can see the basic design, the basic outer shape, and how the heat sources are positioned, or how the component is positioned in accordance to the heat sources. And that's basically the start from where we went into the physics-driven engineering using ToffeeX, and yeah, using the benefits of it.
Yes, thanks, Mattia. I might get started. I might take the lead a little bit from here, just to briefly explain what is ToffeeX and why we found this suitable for the current application and the current project. Indeed, what you are seeing here on the screen is a fast forward of our an animation of the topology optimization taking place. What ToffeeX does is providing a software that supports engineers and designer in designing components that are very performant, accounting for, as in this specific case, specific material properties that might be even innovative or case-to-case specific, and bring them in a very fast way to get a performance solution. The way we approach this generative design is by applying, by solving and by taking into account the fundamental physics that is going on. So it is the physics that is driving the design. You might clearly recognize in this example of a circular cold plate where we have the inlet in the center of the circle and the heated plate on the bottom, how the optimization leads to a system that resembles very well, that resembles very closely a bloody vessel system. So we end up with bio-like solution most of the times, but this is not something we impose. It's because the nature is, after millions of years of evolution, defined the best possible way of optimizing heat transfer with the lowest possible pressure drop, and this is what we are, what our software comes up with. So this is an example. In the specific context of the present project, Matthias, you might jump first slide. We basically applied this technology to the cold plate, to a cold plate for electronics cooling, basically. And the way we conceived our software is for design exploration. And this means that you are free to select the objectives of your design. So your design is typically, you typically want it to be performant in terms of low pressure losses, but of course you want it to optimize, you want to make sure that the temperature you reach is not too high, so you want to have a target temperature, or you want to maximize the heat transfer and maximize the heat rejection of the component to keep the temperature under a certain level. You can play around with all these objectives and build your a multi-objective optimization, and ToffeeX helps you in getting to this design. So basically, through our platform, you can simply input your operating conditions and the design domain you have available, which is what Matthias just shared, where the heat sources are, and regardless of the, and you basically upload also the material properties, like the Constellium CP1, for example, in this case, and you will end up with a shape that is optimized for your specific requirements. Of course, this is left a little bit in the hands of the designers, so you can build your Pareto front with prioritizing pressure losses over heat transfer objectives, for example, and you can basically shortlist and select the best designs for your specific needs. And yeah, basically, this is the Fraunhofer Institute got the opportunity of playing with our software, and they managed to obtain different designs that leverages the different physics and the different materials that we just described. Yes, if you can go on one slide, Matthias. I think that's the last slide of my end, I guess. Basically, in this specific context, we wanted to take two different physics regime, if we can say so, in the sense that on the one end we had the cold plate, in which we had a liquid cooling solution. So basically we had water that was pumped through our domain, and we needed to cool down three different heat sources. And at the same time, what we wanted to do is to accommodate for also some heat sinks that was needed to cool down one additional sources by natural convection only. So the physics involved here is very different, in the sense that in the one case we have a buoyancy-driven flow and also strong 3D structures. In the other case, the solution was more two-dimensional like, and it was more pressure-governed flow. And within a single framework, we were able to include all of the different physics and optimizing for all of the different, but by including all the different objectives, we were able to come up with the solutions that accommodate all the requirements of the designers.
Yeah, thank you, Nicola. I think I'm gonna go on from here.
Yes.
Yeah, and just show you basically what I done. I just want to make sure everybody understands I was a first-time user with the software, so it was completely new to me, and everybody who does CAD design knows it is quite challenging to get into a new software, a new simulation software or CAD system. But this one actually, as you've been shown by Nicola, is actually quite simple, quite easy to get into. It needs some preparation, but at the end, it can save you quite some time. I'm used to designing a lot of different temperature or thermal solutions for tooling applications and stuff. Most of the time, I'm running different iterations in between CAD design, changing the CAD design, running simulations, going back and forth. So it can be quite a long process. And for us, it was interesting. The interesting thing about ToffeeX, you have the optimization within your simulation process. So maybe just to give you an idea. The workflow is for me as a CAD designer rather simple. I used Creo for this project. You can use every CAD software I think there is out there. You start by creating your design space. Then you basically design from there on your boundaries, where you definitely don't want to have any optimization, where you have like a solid wall, for example, parts they don't need to be altered during the process. Created the heat sources with their precisions, and then you load all these using, back then it was still an STL, into ToffeeX, and you start your preparation from there. That's also where you input your material data. And we run different simulations in the comparison Silicon 10 and Constellium CP1. And I think for the liquid cooled side, I ran like 25 iterations within a couple of days. So just to get an idea how Toffee works and how we can improve from iteration to iteration, going back and forth. So it was a rather quick, I have to say, getting in between to design changes and going back to the simulation and checking the results. As you can see, the flow at the end, you get sort of like a negative of the part you really want to print. So you always have to go another step and go back into, for us, it's Material as Magics, a software where we can manipulate and work on STL files. And for the air-cooled side, for the natural convection, the workflow is quite similar, not exactly the same, but quite similar. You can see we had the CAD model of the design space, the boundary condition. The design space is a bit different. It's bigger. It's not just limited to the part itself, because you want to have your space where the natural convection occurs. This is shown in green here. You got your heat source underneath as well. And then you can see toffee preparation, this big green cube, it shows you basically the airflow where the heat exchange is taking place. And there, from there on, basically the software grows like a natural solution for the optimized or optimal shape to get your heat out by natural convection. It looks like, I have to say, quite interesting to me. So everybody that's watching how I designed this or watching the design piece, I was really interested to see this organic shapes that come out of it. But also the same way, different iterations, a couple of iterations done in a short period of time. Most of the software is quite self-explanatory. And if you struggle, you can always call Nicolas.
Thank you.
Yeah, as I already mentioned, you get your solution. You can see the solution, the water-cooled design. I hope you can see my mouse moving. The results of ToffeeX in light blue, and the natural convection on your top left corner, and in the middle you can see the water cooling of the cold plate. And I still had to design like the connections inlet and outlet and some top and bottom plates, basically resembling the different shapes, because at the beginning I told you our heat sources are in different positions, different heights. So for us, since we doing 3D printing, of course we have Materialize Magics. I'm sure there are different software solutions out there as well, where you can using bool operation to create your part from the results of ToffeeX, and you got your final printed ready part at the end. And yeah, from there I basically go into printing. For any of you, I hope most of you are familiar with additive manufacturing and printing. At our institute, we're using laser powder bed fusion as a general term. Different manufacturers have different names for the process. You might hear selective laser melting, laser beam melting, laser fusing. I think one of the machine manufacturers is called direct metal laser sintering. It's basically the same process. We're having a metal powder, in this case Constellium CP1, and we're using a laser to melt this material layer-wise in specific locations to create a three-dimensional part. In this case, the cold plate. You can also see for the project, especially for the comparison between the different materials, we use different machines. Some of them we have at our facility. With some other machines, we worked together with other clients of Constellium. They were quite helpful in providing a printed part for us. They were also quite interested to see the difference, of course, and the results of our study. You can see we try to keep an even playing field between the materials. So we sort of made the arrangement of the parts was given by us. You can see the part positioned in the machine on the left-hand side. In blue, you can see the support structure. That's actually quite a bit support structure. We use this specific orientation because we also want to see the benefits that Constellium's CP1 brings in regards of distortion. Anybody actually who's done a bit of work with metal additive manufacturing, distortion and deformation of parts, it's quite a problem. The CP1 is also less drawn to distortion than silicon 10, and you can actually see on your the middle picture, you can see the cracks within the support structure. You can see how the silicon 10 part tries to bend a bit more than the CP1 part. You can even see the difference in surface quality, different colors. Basically, both parts came out really well. You can also say the physics-driven design made it quite easy to print for us. And yeah, from the 3D printing, we went to the heat treatment. Sham told you about the heat treatment already at the beginning. This just gives you also an idea, just the rather quick and simple heat treatment we used for CP1. So it's 4 hours at 400 degrees. That's rather simple. For the silicon 10 part, we went with the conventional T6 heat treatment. It's widely used for casted parts. We still use it at our facility. I think a lot of manufacturers or additive manufacturing providers use a different heat treatment. They also just do an aging afterwards, so they don't use a two-step T6 heat treatment. But in this case, you can see you can even have an improvement in heat treatment time or time. Yeah, and now I'm going to introduce you to the results and the testing we've done. For us, it's always interesting to see, does a component actually survive? Does it hold? I designed the component with a lot of pressure in mind. It's not necessary for the application for us to see. It's quite interesting to see the material properties. Does it work? So we went for wall thickness. Most of the parts, or for this part, is the 1.5 millimeter wall thickness. It's quite thick. But it was interesting to see, is there a difference between the materials? Does it hold? Is it pressure tight, or does it even burst or something like that? So what we did, it's rather simple test. We basically put in water and pumped up the parts up to 20 bar, holding the pressure for 30 minutes. We had no leaks, no cracks, no nothing. Both of the components survived the torment, basically, and we didn't have any significant pressure loss over time. So we can say both components came out okay. And from there on, we went to the more interesting thermocate testing. And you can see the setup we used, as shown at the beginning, 4 different heating elements. One smaller one, 50 watts for the natural convection, 3 bigger ones, 80 watts for the water cooling. We had a laboratory power supply to regulate the heat input. So all the different experiments run exactly the same. We set like a sharp limit of 30 volts for the heating elements. And these PDC heating elements behave quite similar to let's say computer unique. The better the cooling, the more power you can put into them. So in this case, the better the cooling, the more power draw basically of the heating elements. And we had also a chiller to try to keep the cooling water at the level. But still with this little unit, we had like a fluctuation between 18.5 and 20.6 degrees of the cooling. But again, we timed all the different testing so that we compare apples to apples and compared the same values for silicon 10 and for the cold plates made from CP1. We had a flow sensor in there as well, and we had some temperature gauges as well. So we checked all the values we needed to have a comparison with the simulation at the end. And yeah, also did some thermal imaging. I think the results are also shown later on, just to give you an idea. From the thermal performance, both of the system behave quite similarly. This is not really, how can I say? It's not really a surprise, since ToffeeX is using the different parameters, material parameters, to create the perfect design for the material properties and for the in the way of pressure loss and thermal performance. So it's just normal that the values are quite similar. Still, we see a bit of difference. in temperature difference in the inlet and outlet, specifically for the CP1 and the silicon 10, using the exact same settings. You can see the CP1 performs a bit better. It's only a temperature difference between inlet and outlet of 6%, but it allows a bigger power draw. So if this would be computing unit, you can basically have more computing operations. Also, you could basically run your CPU faster by 6%. And that at the end can be quite a lot. You can see there the power input we used, the current was drawn, and all the values basically comes down to it's not that significant, but there's quite a difference for us. Interesting to see between CP1 and silicon 10. Yeah, and an improvement about the conventional silicon 10 by using CP1. Yeah, and as I told you, you're going to see the thermal imaging of both components. You can see behave quite similar. You see a slight difference in the flow of the cooling because the designs ToffeeX gave us for the two materials are a bit different. But you can see that behaving quite similar. So thanks to Toffee, for both of them, we created the best possible solutions. Yeah, and that's already our short walk through our project. I hope it was interesting for you, and maybe you have some questions.
Thank you very much, Matthias, for your presentation. Indeed, if you have questions, please drop them in the Q&A. I would like to make a further comment on the final performances that, as we all know, typically the limiting factor in cold plate design, rather than the conductivity of the material, is more related to the interaction with the fluid. So having an additional 6% in terms of performances and heat dissipation is kind of a big win in this context, because not only we could have we had, and maybe Sham can comment on this later on as well, in the like an idea of the costs at the end of the day in terms of comparison with the other more standard technique, with other material, like some reference to give you, but we also had an increase in performances. So this is a very good success for the sake of the project.
Yeah. I mean, I also maybe can say something to the numbers. We had an increase in performance, and since we can print the CP1 faster, there's also an improvement in costs at the end, not just performance. Yeah. I think, Sham, your microphone.
Yeah, Sham, I think you're muted.
Sorry for that. So you're right, Nicola and Matthias, because one of the biggest challenge for aluminum additive manufacturing components is the cost. You can think about numerous applications and possibilities, but at the end of the day, if you are able to bring down the cost of the component, this is where CP1 really shines. I mean, you can print at higher productivity, that thereby you can reduce the cost of the component. This will really boost the industrialization of such technology.